Yeah, so we would wait for 2 more minutes and yeah, then we would discuss it. Since it was already published, I think we can go to the discussion part after 2 minutes. I hope everyone has the Replit link. You all have joined. If someone has not yet joined, I can reshare the link. Please unmute yourself and acknowledge that. Okay, so let's start the discussion now. So basically, before moving to the coding part, uh, see what is actually asked over here. So if you, what is a stack? A stack actually follows the last in first out concept, right? That whichever element is inserted at last in the stack, every pop should actually also remove the element which was inserted at the last, and in that specific order only, right? So stack actually follows our leaf order, last in first out, but a queue follows the first in first out order. That is the simple, the one which got inserted first would also be removed at first. Fine. So you have to implement a stack like behavior, but by using two queues. So how to do that? If you see, so let's say I have two queues. Fine. I do have two queues like this. So this is my Q1 and this is my Q2. And fine. So let's say I insert a value 10 in the queue, fine, and I would insert it in the Q1. So this is the front is where I insert the value, from where I insert, because Q in one end you would insert, in that from the other end you would take out, right? So from here I would pop the values. Okay, so my 10 would be inserted over here in Q1. Okay, fine. But let's say after that I have to insert 20, and mind it, the whole thing over here must behave like a stack. This Q1 Q2 module together, I have to make it like a stack. So that's the ultimate motive. Okay, so next value is 20. Okay, 20 is inserted. So I would, since the Q1 is a queue, so obviously 20 would be inserted where? Over here, right? So what would be the condition of the queue in this case? 20 and then 10, right? But now say I have to pop it, correct? I have to pop it. So which one would be popped? If I do a pop, the 10 value would be popped, right? It would be moved out of the queue. But then it is not behaving like a stack. If I want to behave it like a stack, I must actually pop the 20 value, because it was inserted after 10, and stack follows last in first out. So how to do that? That is what the question is asking. So how will we do that? See, the idea is, whenever we insert a value, we would use the second queue as a tool to bring all the values in the proper order. So let's take an example. So first 10 was inserted, right? So put 10 in the Q1, that is fine. Okay. And after that, when you, so after putting 10 in Q1, you just copy 10 to Q2. Okay. Put 10 in Q2. Fine. Okay. Copy means you just move it out. You move it out to, that is, you pop it out. You pop Q1 to the element in Q1 to Q2, that is 10. Okay. Next, what we will do? 20. So 20 will again come to, let's say, my Q1. Okay, 20 comes over here. Now see, what we will do is, ideally, if it is a stack, so let's say this is the stack which I want to actually simulate. So in that case, if this is the end from which pop will occur, so 10 and then 20 should have been the situation, right? So rather what I would do is, I would pop this 10 from Q2 now, right? And I would insert this into Q1. So pop, which was earlier there in Q2, and insert that into Q1. That is DQ from here, or DQ or pop, whatever you want to say, UE, and then NQ it over here. Okay. So what we will get? Let's check. So since I NQ'd the 10 over here, it would be 10 and then 20, which is what I wanted. Now this Q1 looks like a stack. If I pop it, 20 will be popped. So let's take another example, 30. Okay. Now see what we will do. Whichever queue is empty, every time I would use one queue as the alternate queue, either Q1 or Q2, to use it to sequence the other elements in the queue. So initially my 10 was in Q2, right? And then I inserted Q20. So I used Q1 to reorder the elements in Q2. And now see, Q2 is empty and Q1 is already filled. So I would use Q2 as the alternate queue now. Getting the idea? See, let's go through some iteration and then you would understand. So next we get 30, right? So we would put 30 in the queue which was empty. So this is empty, right? Q2 was empty. So put 30 in it at first. Okay. This is the end where NQ happens. So I put 30 over here. After that, what I would do is I would DQ, same step. I would DQ all the elements from Q1, which was there earlier. Okay. And put them and NQ it in Q2. So every time you push an element into this modular stack, what essentially you are doing is you are dequeuing the elements which were earlier there in a queue and enqueuing it in the other queue in order to get that effect. So what will happen if I dequeue the elements of Q1 now and enqueue it in Q2? See. Sorry, I stopped sharing, just a second. Yeah. So what would happen? Obviously 20 would be popped at first because this is on the popping end, right? Like a queue. So 20 would be popped at first. So 20 would be inserted over here and 30 was already there. Correct? After that, what would happen? So 20 is not here anymore. Yeah, 10 is here. So I would continue this popping from Q1 unless and until it becomes empty. So again 10 is popped and 10 would be inserted over here. Fine. So what is the state of my queue now? 10, 20, then 30. Okay, let's take another. Now see, now my Q2 is filled and Q1 is empty. I told you that every time a particular queue in one iteration, Q1 would be filled and Q2 would be used to order the elements. And in the next iteration, Q2 has already been filled and that's why Q1 would be used to order the elements. Right? Alternatively, they serve the purpose of ordering and storing. So now let's say 40 has been inserted. So at first I would put 40 in the empty queue over here. Done. And then again same step. DQ all the elements from the one where the other elements were stored, earlier elements, and NQ it in the new one. So again I would DQ and obviously 30 would be popped at first and 30 would be inserted here at first. So I would get something like 30, 40. Fine. So 30 is gone. Now 20, obviously 20 is the next one. So 20 would be enqueued on the left hand side. So again 20, 30, 40. And finally likewise 10. So if you see now, if I pop at any time from this queue, so this is the state of this queue, right? This is empty now. And this has become 10, 20, 30 and 40. So if I pop at any time, I would be popping 40 from this queue, which is what a stack would have done because 40 was the last element to be inserted. Then again, if I pop, then 30 would be popped in a stack. And this is only this, that would only happen in this queue as well because 30 is just after 40. Fine, simple concept. So you use two queues every time you pop, push an element. You actually use the other queue to order the elements. And the way to do that is simply dequeue the elements in the earlier queue and enqueue it in the newer queue. In the next iteration, the Q1 would serve the purpose of Q2 and Q2 would serve the purpose of Q1. Right? So one queue is working for storing the data, other queue is working for arranging the order. I mean, how you do the arranging? Simply by enqueuing and dequeuing. That's it. Okay. So that is the basic concept. Is the basic concept clear?
So can you explain it again, like what we are trying to make it a stack, so should be like in the different iteration. How is it
Yeah.
working?
Yeah. So I would just repeat it. See, so uh, let's say we want to make a stack, right? But by using queue. So what we do is, so let's say 10, 20, 30, 40. Fine. So 10, 20, 30, 40, this 10, 20, 30, 40 is the sequence in which data are inserted into the stack. Let's say this stack, whole stack. Fine. This whole module is a stack, right? The set of these both queues. So if that is inserted in a normal stack, what would I want if I do a pop after at this point? If I do a pop, let's say I do three consecutive pop at this point. What would happen? First 40 would be popped out, right? Then 30 would be popped out, and then finally 20 would be popped out. That's what I want, right? If it is a stack. So last in is 40. So first out should be 40, like that. And in that specific order only. So that's what a stack would have done. But how can I generate the same effect using queue? So the thing is, I would use two queues. And I'm again going through the iteration a little faster this time. So what would happen? So at first I would put 10, which is the first element, right? I would put 10 in the Q1. Okay, fine. And see what would happen. Now, since this is the first element, it doesn't matter anyway, because if I pop it now, 10 would be popped in case of stack and as well as in case of this queue only. No issues in that. So let's say if I put only 10 in a stack, there is only one element and then I pop it. So 10 would be popped out only. And same thing would happen in the queue as well because there is only one element. But after this, let's say you have to insert 20, right? So what I do is I use the other queue, which is not empty now, sorry, which is empty now, to put the value in that at first. So these two queues would serve two different purposes. One of them would store the current elements which are already there. Other would only store the new element which is now pushed, right? And the queue which was storing the earlier elements would then dequeue all of them and put in the new queue. So what I mean is 10 was there in Q1. After that 20 is inserted. So I would insert 20 in the queue which is empty, right? So Q2 is empty now. So I put 20 over here. Okay. Since it is a queue, the insertion must happen on either one of the side. I am taking the head to be the side where insertion would happen. Okay. So 20 is inserted over here. Fine. Now, what I would need is if I do a pop and I want to simulate a stack, then 20 should be popped out, right? But now 10 and 20, both of them are in two different queues. So I want to place them in a specific order and that order being 10 and then 20 because that's what a stack would have done because 20 has been inserted after 10 and that's why any pop would result 20 being popped out first, and then second pop would pop out 10, right? So what I would do is, in order to have this order, I would dequeue the element which was earlier inserted, right, in Q1, and enqueue that in Q2. Why I am doing that? Once I pop, so 10 would come out from here, from the rear end, and enqueue would happen over here, right? So 10 would be enqueued over here. So the new state of my Q2 would be 10 followed by 20. Okay, now 10 is not here. 10 is already dequeued. Now see, if this is the order of Q2, now if I do a pop, obviously 20 would be popped out first, because this is the place from which pop would happen in a queue. Right? 20 would be popped out first and followed by 10. That's what a stack is. Correct? So if you take another example, let's say I want to insert 30 now. So which one is the empty queue? Obviously Q1 is again the empty queue. So I put 30 in the empty queue now. Okay. And now what I do, I use the queue which was storing the earlier elements to dequeue them and enqueue that in the newer queue. Same steps. So now the queue which was storing the earlier element was Q2. It was storing 10 and 20. So I dequeue all the elements of Q2 and enqueue them in the new queue, which is the Q1. So what would happen? Obviously 20 would be popped out first, and then 10 would be popped out. So 20 is popped out first and enqueued in Q1, and 10 would be popped out and then enqueued in Q1. So what would be the state of Q1 now? 10 and 20s are popped out.
10, 20, 30.
Yeah. I'm just clicking on that mistakenly. Yeah. So 10, then 20, and then 30. Now if I do a simple pop on Q1, obviously 30 would be popped out first, and then 20, and then 10, and that is what a stack would have done, right? If you insert 10, 20, 30 in a stack and simply then pop to make two pops, right? So obviously the output should be 30 and then 20. Here also that would happen. Even though it is a queue, if you pop from here, obviously 30 would be popped, then 20 would be popped. Fine. So simple idea. What you are essentially doing is, every time you push an element into the this module, this stack module, right? This whole stack module. Every time you are pushing, you use one queue to store the current elements and the other queue to actually reorder by simply making a sequence of push and pops. That's it. Okay. So yeah. So that is the concept behind it. Now if you go to the code and just write this. So I have to write a code, fine, to make the stack work. So basically I have to implement which functions? I have to implement push, pop, top, and empty, is empty. Is empty is quite nice because quite easy, because you have the size parameter in the stack already given. So what only I have to do is simply define this is empty. Okay, and then simply I have to check if self.size equal to 0. Then you simply return true, it is empty. Else you return false. Fine. So that was is empty. Next function is top, right? Top I would come later. So let's discuss the complex one first, the push function, right? Because push was the main discussion that we did. So def okay, push and data. Fine. So after that, what I have to do is now just think about the discussion that we did just before. So first, what we would do, can someone tell me? Acha, so let's write the first line. Obviously, since I'm pushing the data, the first thing that is quite intuitive is I would have to increase the size, because this push means I'm pushing into the stack, right? This is a function. The push function is a part of the class stack. So when I'm pushing a new element, I must increase the size of the stack. So what I would do is I would increase the size at first. Self.size equal to self.size plus 1. So this is the first thing that I need to do. And after that, what I need to do is you remember that you put in one of the queue, right? You first put the element in one of the queue, and then you actually pop from the other one which was initially storing the data. Okay, so I'm assuming in the first iteration q1 is the one which was storing the data. You can proceed it anyway. Okay, so I would just put the new data in one of the queue, which is, let's say, q2 in this case. Fine. Now q2 is there, q2 dot enqueue. I'm using the function which is already defined, right? If you see in the queue class, enqueue and dequeue is defined, so you use that. Okay, I enqueue the data. Fine. So now first I have inserted that into one of the queues, the empty one, the empty queue, right? And now the other queue which was earlier there, I have to dequeue all the elements from there and put it in this q2. Correct? All the elements from q1 which was earlier there. Now in the first iteration, there would be no elements, but let's assume we are in the middle of the some iteration and there are elements in q1 already present. So I would just pop all of them one by one until q1 is empty and put them in q2. So I have to pop until q1 is empty, correct? So simply check that when q1 is empty, so I would use a while loop to make q1 empty. Okay. Empty, just unless and until it's empty, you run it. Fine. And what I would do is, at first I would simply dequeue, right? So I'm dequeuing, and then what I need to do is I need to enqueue that into the new queue, which is q2. Correct. So I would just simply enqueue this value that I gained by dequeuing from q1 into q2. Yeah, so that's it. So simply put the data into one queue that I did in line number 23, and then whichever was present in the other queue, you simply run through the whole queue unless and until it becomes empty, dequeue all of them, right, and then enqueue that in the newer queue. But if you go over here, when we are going through the iterations, right, so in the first iteration, q1 was serving the work of storing the data and q2 was doing the enqueue dequeue operation. In the next iteration, now q2 was storing the data and q1 was actually performing the enqueue dequeue operation. So basically what's happening is, in every so let's say in the 40, let's say at this stage I insert 40, what would happen? So 40 is inserted, right, at this stage currently. So obviously I would insert 40 over here at first, and then I would dequeue all the elements in q1, right? So my q2 would become after that 10, 20, 30, 40. Okay, 40, and my q1 would have become empty. So after that, if I insert 50, now q1 would be stored, 50 would be inserted in q1 at first, and now enqueue dequeue would be performed by q2 actually. That all the data from here would be pushed from here to here, right? So in every subsequent iteration, the purpose of q1 and q2 interchanges. right? So that's what we need to take care of. That thing we have not written yet, because here I am assumed that Q2 is the empty queue, and that's why I'm entering the new data in Q2 at first, and then I'm dequeuing all the data from Q1, assuming that Q1 stores all the data. But this would interchange in every iteration, right? So what I need to do is, once this while loop is empty, in the next iteration I have to change it, and that's why I would simply swap these two queues. That serves the purpose, right? If I just swap the two queue names, right, the data they are storing. So what I would do is I would just use a normal swapping. Let's take another queue, a temporary queue only. Okay. To equal to okay. Yeah. So I have increased the size one. I've enqueued it into a queue, and yeah, this should work because I'm interchanging it here. So that, yeah, this is the push operation mainly. And now we would discuss the leftover two operation. Before going to the both of them, anyone has doubt in the push operation, please ask.
So this interchange has to happen every time, every iteration.
Sorry, can you repeat once again? Every push, right? Every time you push it, the function of that changes, correct?
So even if there are single pushes, then also you will have to interchange the labels Q1, Q2.
Yeah,
Like,
yeah,
okay.
yeah. So only in the trivial, so this would be trivial in the first insertion only, because see, uh, so when the queue, both of them were empty na, in the first iteration, first insertion, when I inserted 10, right? So then it doesn't matter. I mean, what would happen essentially, you would insert it in Q2, because that's what the code does. It assumes Q2 is the new one. So 10 would be inserted in Q2, right? And yeah, then I would pop all the elements from Q1 in the loop, right? You remember in the loop, right? This loop. I would all pop the elements from Q1.
Yes,
But
sir.
yeah, but that's trivial. I mean, there are no elements in Q1 since this is the first iteration. So nothing would be popped. And yeah, so 10 is only stored in Q2 only. After that, when you insert 20, what would happen? 20 would be coming over here, right?
So by that time, the labels will be exchanged.
By that time, yeah, exactly. But where did I insert it? I insert it in Q2, correct? My code is inserting at self.q2, but we just discussed that when I insert 20, I need to insert it in Q1. So how the code would work? Getting the point? I'm in the dry run, we are inserting it in Q1, but my code is inserting it in Q2 every time. So in order to make it happen, I'm just swapping the Q1 and Q2, the label change, right?
Okay, so you are just having the same effect by label change.
Yeah. Just changing the label, because this code I cannot change every time, right? For one, you can do that. I mean, let's say for the first pop you self q2.enq, and this one you write self.q1.deq, fine. You then check if it is an even number of pop, right? Let's say for every pop you maintain an index for subsequent even and odd numbers. So if the ith pop is even, that is I is even, right? You count the number of pops happening, and sorry, not pop, push, the number of push happening. And if the ith push is even number of push, right, then you maybe put it in Q1, and if it is odd number of push, you can put it in Q2. I mean, that just you have to write two if statement and kind of copy the same code. I mean, this is a much elegant way to do the same task, right? Only thing, you are interchanging the work of both the queues in every subsequent iteration. So anyway, you can do that. You can make a counter and check if it is the ith iteration or I plus 1th iteration, and accordingly push it in Q1 or Q2. Or you can simply interchange like this and go. Right. Idea is clear, right?
Yes, sir.
Yeah, fine. So okay, so that's done, and then other two are fairly simple. So obviously, since we discussed that every time you pop from the right hand side, so it's actually easier. So simple pop is I pop it if the queue is empty. So that check we can do, right? If so, you see if the stack is empty, return message stack is empty. So I need to check whether the stack is empty, and that we can do by simply using this size, right? This size attribute that we had. So check that if self dot size equal to, let's say, not equal to 0, then I would do something else. I would print what is the sentence? Stack is empty. Okay. Oh. And in the if I have to actually, since I'm popping, so now I have to decrease the size. So size minus equal to 1. So the size is decreased, and now I would just since dq is already defined for my queue, right? So I would just use that. See, keep this thing in mind. See, I am dequeuing from Q1, but that would work every time. The reason for that is I'm changing this Q1 Q2, right, after replacing. Otherwise, here also, if you do the if condition checking by making some counter variable to check ith iteration, I mean which iteration is this, which push is this, then accordingly you have to also modify the pop operation accordingly. That because you are not swapping the queues, you are just pushing and popping into two different queues. So accordingly, you have to apply that logic in pop as well. If you do that way, if you do in that way. Okay, so dq we have done. Which one was left? Is empty top, right?
Sir, won't this cause a problem if we are decreasing the size before we are dequeuing in the if statement?
Sorry, what did you say in the if statement?
We are decreasing the size before we have dequeued from the Q1.
So see, actually, I mean, yeah. See, we are doing this on a single normal program, right? It's not multi-threaded or something like that. Where so what I mean is, if I'm decreasing it over here, so if line number 32 is executed, I can guarantee line number 33 is executed as well. No one would come in between. And if you see the DQ operation over here, it simply pops. So size is just a measure of whether the queue is empty or not, right? And yeah, so it's just simply I'm using in the DQ operation, it simply pops it. So yeah, it would not make a difference. But if you execute these kind of statements in a multi-threaded environment, then you must ensure that both of these statements are kind of atomic. That is, if one is executed, the other must be executed. Otherwise, your size would be decreased at first, but maybe the DQ did not happen at that point of time, and some other operations came in between. So you can land up in trouble. Yeah, but yeah, I don't know whether you asked it from that perspective, but that can happen, and that's where you use atomic or synchronized way of execution. But if you say it in terms of normal programming, so here you see that DQ is simply a pop operation from the list, right? So yeah, that doesn't make much difference. Okay.
Yes, sir.
Fine. So top, right? So top operation, what we have to simply do, we have to return the value of the uh, I mean, whichever is there in the top of the stack. So here you do not have stack. So basically the Q is from where we are popping. That is my Q1. From there I would just return the top. Top means, remember this, the last element, right? From where were we popping? We are popping from the right hand side, right? So this last element is actually the top, correct? So how can we refer to this element? By simply using -1, right? In the array, sorry, in the list indexing. So we would use that. And again, we have to check whether it is empty or not. So if, what was the name of the function that we defined? We can also use size, but let's use is empty only. If self dot is empty, right? Okay, so let's do the not case first. If it is not empty, then I would return the name of the this items, right? In the list, the last element in the list, I would return that using -1. And otherwise I would what was told to be printed, top stack is empty, right? So simply return Acha, it says return, right? In the initial one I think I printed it. I should return it. Fine. Yeah. So top, pop, push is empty. 4 functions defined. In push, what we did is we increased the size, and then we used it to insert. Yeah, until unless it's getting empty, we are popping from Q1, enqueuing it to Q2, and then for the next iteration only, sorry, for the next pop, we are exchanging the labels to exchange the work that they are doing. And pop -1. Yeah, fine. So let's see. Okay. Okay. So again, any doubt regarding this question? Please ask.
No, sir.
Fine. So again, we have one more question here, which we did not discuss yesterday. So that would be week 4 problem 2. Okay. So at least try it. That was also published yesterday only. Please try to do that, and we would not wait for long. Right. After 5 or let's say 7 minutes, we would discuss that, and then we would go to the general discussion of the content. Fine. So yeah, so here's the question. Yeah. If you have any doubt in understanding the problem statement, or the basic thing that the question is asking, if you cannot understand, please ask me. I would try to address that, and then we would do the code. So at least have try to think how you would approach this problem. Huh? So since we would discuss it after say 5-7 minutes, I would at least expect some of you to speak up what would be the approach to solve this problem, even if you do not code it up completely. Try to code as much as you can, but at least tell us the approach that you would use to solve it, huh? After 7 minutes. Okay, so 2 more minutes after that we would start the discussion. I would at least expect a few answers of the approach that you would follow to solve this. Yeah, okay, fine. So let's start the discussion. So anyone wants to say how you would approach solving this problem?
So we can start from each node, perform a breadth first search, and keep a visited counter maybe. So whenever we are visiting the nodes, we can keep a visited counter, and as soon as it in any level we find the other end2, so we can stop the BFS and mark that as one path, so can be repeated. So the node that have come in the path, they can be marked as visited, like in those things maybe.
Exactly, exactly. Yeah. So what we do in normal breath. Acha, first of all, a few answer questions to that. Not questions, few points. So you use a BFS because here you would get the maximum number of possible route it is asked, right? So you can use BFS to actually get multiple multiple paths, maybe of different length to the given particular uh, end two, right? The from the source to the destination. But the thing is, BFS would actually give you the optimal paths possible every time. So given a set of vertices, using those set of vertices, if you can reach to end 2 from end 1, then BFS would give you the shortest possible paths. Okay, so that is one important point. Now, another important point is, obviously here you may get, so if you take this example, the sample input, this one, right? So here you can see that you have got three possible paths from and between 0 and 1. So two of them are of length 3, whereas one is of length 5. Right? No, I mean not 5, sorry. Two of them are of length 2 edges are there, and other one is 4 edges are there. But the idea is, see, although it is of 4 edges and BFS is still giving that as an answer, the reason for that is when 3 and 6 in the first two paths, 3 and 6 were already used up, right? And the question is asking you return the possible part in the inductor without going through the same node again. Okay, with exception to n1 and n2, because yeah, you are going from n1 to n2, then coming to n2 from n1. So obviously n1 and n2 would be repeated, but other than n1 and n2, the all the nodes in between must not be repeated in the different paths that you are printing. No, sorry, not the paths you are not printing. I mean the different parts that you are working upon. Okay, so since you have deleted 3 and 6 after you have exhausted moving from these two paths, that's why if you remove 3 and 6 from this graph, I mean remove these 3 and 6 nodes in the path to reach from 0 to 1, then the length of the shortest path would also be 2451. Okay, so the length would be 4 edges. So although you are using BFS, so this is one important and subtle point to notice. So otherwise you should have asked this question, that BFS would actually run through the shortest number of the smallest path, right? The paths which are smallest. Now both of these two paths are of 2 edges each, so that is understandable. But why BFS would produce a result like this? Okay, which is longer. The idea is, since 3 and 6 are removed after you have exhausted both of these paths, so use, other than using 3 and 6, if you use the other nodes, right, then obviously it would be a path of length 4. Okay, so that's why BFS is used. So the main idea is you use BFS in this program. As I don't know your name who said the answer, but thanks for that. So we will use BFS. Only difference is, see, we will use BFS multiple times, right, in order to find all the possible paths. Only thing is, in every subsequent iteration of BFS, we have to make sure that we do not use the vertices which has already been used in the earlier BFS that we have done. Got the point? That should not be in the path. Okay, so corresponding to this graph which is there on your screen, the minimum path length would be 2 from 0 to 1. That's why the first path 031 was chosen. When you remove 3, next is 160, again a path length of 2, that was chosen by the BFS algorithm. But since again that is all 6 is also removed, then there would not have been any path which is of length 2 or 3. The only path, shortest path between 0 and 1 that would have left is of length 4, and that would be 02451, and that's why BFS has given you that as the result. Okay, so this code is essentially simple BFS, only with an added condition is that you have to run the BFS multiple times unless and until you exhaust away all the paths that can be there from the end 1 to end 2. Restriction being, in every path that you get, you should not repeat the vertices that is already been visited in another path, right? Okay, so that is the idea. Is the idea clear, or should I take an example and again explain this? Please clear the concept, otherwise, see, unless and until you are very clear about the problem statement, you cannot code it up. So if you have any doubt, some of you any doubt regarding this, regarding the understanding of the problem, please ask. I would again do a dry run of the thing that we just discussed. Is it okay? Then I suppose it's okay with everyone.
Yes, sir.
Okay, fine. So then let's try to code the thing. Okay, so this is the function that is being called back and forth. Anyways, so it takes the source, destination, and the adjacency list of the graph. So let's go one by one. So what is the first thing that we have to do? First thing is we have to at first run one BFS. At least once we have to run BFS, and in order to calculate a path, right? In order to get a path from end 1 to end 2, what did we do in the previous coding also for this week 4 in the live coding? We initially ran a BFS algorithm, and that BFS algorithm was returning us two dictionaries, the one being level or visited, and the other is the parent one. So we use the parent dictionary to actually calculate, to actually find the path between two vertices, any of the two vertices, from the starting to any other vertex, right? So how we did that? We simply recursively or iteratively, either way you can do. You actually check the parent of the destination, and then the parent of the parent of the destination, then the parent of the parent of the parent of the destination, unless and until you reach to the source node. So once you reach the source node, you get the path, right? That is the idea, and that is shortest. The reason for that is you ran a BFS algorithm. So the parent dictionary which has been returned to you is always storing the minimum number of hops between two vertices. Okay, so first we will have to run BFS. then obviously as a result of BFS we would get one parent and one visited dictionary, visited or label, whatever you use, fine. And using the parent we would actually calculate, we would actually find the path. Now once we find one path, in this code we have to actually find multiple paths, right? So once we find one path, what we will do is we will rip out all the intermediate vertices from that path that we found, okay? And then again when we call BFS next time to calculate other paths, we would somehow ensure that these vertices, which is a part of the first path, is not calculated while running the BFS second time. Again, so second time we again get a new dictionary of parent and label, right? And in the second iteration of BFS, again we find the path, the second path, and again we check out all the vertices, intermediate vertices from the second path, and in the subsequent, again the third call of the BFS, we would add those vertices so that those vertices are not considered in the third attempt of running the BFS, right? So with every subsequent attempt you find the path, you pick up all the vertices from that path and somehow tell the BFS algorithm how to do that. We will discuss that in code. Somehow tell the BFS algorithm in the next iteration that please don't consider these vertices while you find the path. Okay. So there would be some point you would reach where BFS, because every iteration, every BFS, you are actually eliminating the vertices, right? You are finding a path, you are eliminating those vertices in the second run of BFS. In the third run, you are eliminating the vertices that you found in the first and the second run. In the fourth run, you are eliminating the vertices you found in the first, second, and third run of BFS. So every iteration, you are actually restricting the BFS to use lesser number of nodes in the graph. So at some point, you would reach that when BFS is not able to reach from N1 to N2 because the number of vertices which are left to it are very less. There is no path from N1 to N2 considering only that much lesser number of vertices. Okay, so that is the point where you would terminate the algorithm. Okay, so how can you judge that? How when to terminate? The condition is in that situation you cannot reach the destination, right? So what would happen? The visited of N2 would be false, that it's not visited even after running BFS, right? Even after running BFS, if you get the visited of N2 as false, that means in the last BFS we could not reach to N2 vertex from N1 vertex. So that means you have exhausted all the paths. Okay, so that was the overview of the code. Now let's go one by one and write it up. Okay, so and yeah, the question asks you to ultimately print the number of paths, not the path themselves. So we would obviously use a count variable. Every iteration that we run BFS, we would increase the count. Okay, so at first let's call BFS because that's what we have to do. Those of you did not get it, please, it's quite okay. It's, I mean, it would maybe obvious. Please listen to it once again, whatever I said. Maybe if you got it, it's fine. If you did not, please listen to it once again and maybe once more again on YouTube. Fine, you would get it. So at first we would call BFS. We have not defined it. We would define it now. I have to pass the adjacency list. Okay, and the source and the destination. Actually, the source, not the destination. We don't need the destination to be given now. Okay, and as a result, we would get two dictionaries. So I don't level comma parent, right? Actually, let's use visited in this case. It's not required. Yeah, fine. So after that, what we have to do is we have to, let's say BFS has given you the visited and the parent dictionary. Now you need to find the path, right, using the parent. So let's make another function to find the path. So start and end or source or destination, whatever you want to call it. Okay. Acha, one more thing. See, since we are using BFS, in this BFS only one change is there, that we would restrict the algorithm to use all the available nodes, right, in subsequent iteration that we were discussing. So somehow I have to tell that. So let's give that data to the BFS algorithm using a list. So let's call that a what should we call it? Restricted nodes. Okay, restricted nodes. So you are not allowed to use these nodes.
Why are we passing restricted nodes here itself? Like, don't we?
Yeah, I mean, you will define the BFS only once, right? You may not need restricted node initially. That's why you are initially passing a zero, I mean, a blank list. But every time subsequently, whenever you call BFS next time, you have to somehow tell BFS that don't use these nodes. So you cannot have I mean, it should not write two BFS functions. So what I did is simply incorporated the same signature restricted nodes, but first iteration of BFS, we are simply passing an empty list. After that, whatever path we get, we would take the nodes from the path and add it in the restricted.
Yes. Yes, sir.
Fine. Okay. Okay, so one other variable is there, counter, right? We need some counter. Let's name it something else. The path count. How many paths we get till now? Fine. So that's done. After that, what we have to do? Yeah, you want to say something?
Yes, sir.
Okay. Okay, so before going to the BFS and find path and all that, let's see what is the next thing. Let's assume that we have the parent and the visited, and let's say find path has given us, will give us the path. Fine. So what we have to do? First of all, I have to, every iteration I have to find the path, right? And how long will that go? We just discussed that you will be able to find the path unless and until the destination, I mean, sorry, you will be able to find the path until the destination becomes unvisited even after running BFS, right? Because at that point it means that you could not reach the destination using the lesser number of vertices which has been given now, because your restricted node list has grown to certain extent that it actually incorporates most of the nodes, and whatever little bit nodes are left in the graph, you cannot use that to reach the destination from the source, that is end 2 from end 1.
Sir,
Okay,
it means this will be that point when we cannot do BFS further, right?
exactly. You cannot do BFS. I mean, you can do BFS, you cannot reach N2. N2 would be unvisited. That's it. Fine. I mean, you can do BFS, right? Even with a single node, you can do BFS. A trivial run would happen. But only thing is, the node N2 would be unvisited because you cannot reach that. BFS is not able to reach that N2 node because you have there is no path left, because most of the vertices is there in the restricted nodes, and restricted nodes are not, I mean, BFS algorithm cannot use the nodes which are there in the restricted nodes list. Fine. Yeah. So what is the condition? I have to check if my visited, right? We are using a visited one here. So visited of the N2, that is the destination. If visited of N2 is, I mean, true, right? Then you can actually check for paths, right? Acha, one important point is, so we don't know how many times we have to run BFS, right? There can be 500 paths. So we are not running any loop over here. So if is not the correct choice to do that, right? Because if you use if, then again you have to use an external loop to run n number of times, and how many times you would run it. It's better to make this condition in the loop that unless and until you are getting visited N2 as false, please continue the work. Please continue running BFS every time. So let us use while. Okay, and now obviously since visited of N2 is true, that means I have at least got one path. So first thing that we would do is increase the count by 1. Okay, so we got at least one path over here, and then we have to find the path. What is the path? Once we find the path, then we can actually incorporate those nodes into the restricted nodes list. Okay, so who would give us the path? The path would be given to us by the find path function that we have not yet defined. And find path obviously would need the parent list, and the obviously the since you are getting the path, so you need the source and destination. So end1 and end2. Okay, source and end. So let's okay. So got the path. After that, what simply you have to add. So path is also a list, right? You would return a list. So simply add all the nodes which are there in the path into the prevention list or my restricted nodes list, right? Simply add that. So we would use restricted node. Now you can add it any way. I'm using extend. Okay. So now I have taken a path and then added in the restricted node so that the next BFS cannot use that. And now I have to again call BFS for the subsequent iteration, right? With the restricted nodes, with the because initially restricted nodes was empty. Now I would again call BFS, and that BFS would be called n number of times until this while loop fails, which is you are not able to reach the destination. Okay.
So what is the extend keyword doing?
Extend is simply adding. I mean, when you write to extend, okay. So if you write extend, so let's say one list L1 and L2, there are two lists. If you write L1 dot extend and in that you pass L2, what it basically does is it incorporates all the element of L2 into L1 together. Right? It extends L1 by incorporating the elements by putting the elements in L2 from into L1. Okay, so let's say 1, 2, 3 is L1, 4, 5, 6 is L2. You write L1 dot extend L2, that means L1 would become 1, 2, 3, 4, 5, 6. That's it. Okay, so we are simply adding all the nodes in the path list to the restricted nodes list. That's it. You can also travel through it and put dot append. I just did that in one line. You can just write for I in path restricted nodes dot append path. That also works. Okay. Only thing is you have to take care of the repetition. So if in that case already the node is there in restricted nodes, so it's better to check while appending that whether it is already there in restricted nodes, and then you add. Got the point? So if whatever your node is in the path, for I in path you are using, right? So if you can check if I in restricted nodes, then do something else, restricted node dot append I. Got the point? Anything you can do that also. Simply add it.
Extend will not put the repeated elements.
It would check for that. It would check for that, and then if it is there, actually see one important point is their repeated would not actually happen a lot. The reason for that is once you are putting it into restricted node, BFS would not count that. So that would not come in the path as well. Okay. So either way it would work.
Yes, sir. Got it.
Fine. So obviously again I am calling BFS. So parent and BFS. Okay, so count we have increased, and yeah, what else we have to do? So BFS is called, it would actually execute until I am not being able to reach N2. Yeah, and we are executing, increasing the count with every path, right? So only thing is we have to now return the count. Return or print? return it. Okay. Path count. Okay. Fine. Now let's, so the basic structure of our program is ready. So this is the main basic structure, right? Now only we have to make the utility functions. That is the find path and the BFS. So let's do that. Find path is the same thing that we discussed earlier in the, in the previous code of this same week, that you just check the parent of parent of parent of parent like that from the destination to the source. Okay. So at first, obviously, we would check the parent of my destination, and let's say I put that into a variable. So let's call it, what do we call it? Let's say p equal to parent of destination. Okay, not p. Let's call it node. Yeah. So this is the first thing that I need to do. Obviously, I need to find the destination's parent, the penultimate node in the path from source to destination. Penultimate means just the previous node before destination. Okay, so I get that, and after that I would just simply iterate through the parent by using a while loop, just like yesterday we discussed. Okay, while my node not equal to start, the source, and my node is not equal to the source, what we would do is my starting node, I am iterating till that, and then I would simply each iteration I would append it, and I would find the parent to that particular node, right? So I would append. Okay, I'm not taking the list to, let's say, call it, what do we call it, path. Path is fine. And then we find the parent iteration, right? The parent of the current node. So this is basically the parent of parent. In the third iteration, it would become parent of parent of parent. That's it. And then finally, we simply return the path that we got over here, right? In the path variable that we got from here. Okay, so next thing is we have to define the BFS. Now that simple BFS, only one condition that would change is we have to incorporate the concept of this restricted nodes. That's just simple. Whenever we check the if visited num, before pushing into the queue, we would just check if visited and not in restricted nodes. That's it. Only that would be the change that we need to do in the BFS program from the normal BFS. So if we do that, end one, let's say it end only because it doesn't matter. The starting vertex, okay, and my list, restricted node. Fine. Now normal. Set the visited to false. And we have to set our parent to -1, and then initialize the starting vertex, which is end one, visited and parent for starting vertex. Okay, so that we have to do. So visited for end 1, set it to true, and we would put that into the queue. Okay, so queue we have not made yet, so we have to make the queue also. And then while, so I'm not going line by line explanation of this because this is the normal BFS we have already discussed yesterday, and also in the content it's discussed. Okay, so let's say the first node I pop. Okay, so we have popped the first node. Now we have to check the neighbors. So here we would actually check that thing whether it's a restricted node or not. So, but before that we have to traverse the list in order to know that adjacency list. So first we would check the whether it is whether the current neighbor that you are getting, sorry, whatever the current node that you got by popping, who are the neighbors for that, right? So in order to check that, I just need to check the list for corresponding to the node vertex, this node vertex in the dictionary, right, in the A list dictionary. So for my every neighbor, corresponding to the node that I got. Okay, if now here I have to check the visited thing. So if it is not yet visited, right, and now this is the addition that we have to do is, and not in the prevention list, I mean the restricted node list where it is prevented, right, this list. Okay, so I would prevent it to be executed, to be founded in the to be used in the Bfs algorithm. Okay, so the neighbor is not visited, the neighbor is not in the restricted nodes list, which I would use to prevent Bfs to access those nodes in the in calculating the parent dictionary. Correct? That is basically traversing through the graph. Okay, so now normal thing, we would check the visited to be visited of my neighbor to be true, and then the parent of the neighbor to be the node that I got, right? And yeah, and then we would basically append the neighbor. Fine, and once this is over, we would simply return our list. So my visited list and then my parent list. Okay, what is the order where I am storing visited parent? Okay, yeah. Okay, so okay, one thing we did not do, we visited it, okay, done queue. Okay, we have not appended anything in the queue. So first we have to append the end one, right? Okay, done. Actually, it's better to write this below conceptually. So we have visited and then we have appended and then we are continuing the iteration. Okay. What is this error all about? BFS, right? BFS a listed one and restricted nodes. Spelling
Sir,
mistakes.
in A list, the L needs to be capital, I think. In some places, A list, L is capital. In some places, it is not capital.
Acha, 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 okay. Undefined A list. Restricted node is correct. Yeah, fine. Here A list, okay. Okay, so let me check. Okay, once back and we are going restricted nodes is not there. Fine. Then we are calling BFS. We are going till we have while. You can also use if over here, which I was initially thinking to do. But okay, in that case, you again have to run a while loop outside and check whether the end is not visited. So, anyways, it's better to directly put it into while. And path count, okay. Then we are finding the path, which is fine. And then appending it to the restricted nodes and calling BFS with the newer restricted nodes until visited end2 is false, right? And returning the path count. Okay. Yeah, let's see. I hope it should work. Okay, fine. So, any doubt you have, please ask. This was a bit long. You can read it again and check YouTube and I tried to explain what is the idea behind it. Those of you understand it's fine. Others, please try to have a look one or two more times. You would understand. If all of you got it, it's nothing good. Nicer than that. Yeah. Any doubts on this question? Then we will move to the general discussion.
Well, in the find path function, you are essentially looking at the nodes till the time it is like each time you're changing the parent, right? Going through the parent of the parent.
Going from the destination to the source. I mean, yes, first of all, see, that's why I wrote na, parent of destination. At first, I got that into a variable. And then I'm just iterating to check unless and until I, in this process of checking the parent, unless and until I reach the source. That's the essentially the path. And what is the process? See, I'm every time going parent of node into node. So the parent of a node, I am storing that into node, and next time when the while loop runs, it would check node not equal to source, right? So every iteration, we are actually going parent of parent of parent of parent. We are doing that because I'm storing the parent of node into node itself. So in the next iteration, node would essentially be the parent of the earlier node. Yeah. So yeah, that's it.
Okay.
And how many times we would run it? Until and unless we reach a point where the node itself is the source, right? That is, we in the path in the path from of checking the parent of all the nodes, we have reached a point when the node that we got by checking the parent dictionary is the source itself. So that means we have started from the destination vertex, and by checking the parent in the chain of parents in that, we start from destination and we reach the source. So that is essentially your path. Okay. Fine. Any doubt? Any other doubts? Okay, great. So now let's, acha, one more question is there. So I am publishing that now. It's regarding topological sort, right? That's kind of your homework. So all of you should try at least doing that. I have just published it now. Okay, just a second. Yeah, so it's week 4, problem 3. There is a problem on the topological sort, simple topological sort with just one added constant. That's it. Yeah, so please try to do that. And if you have any doubt on that question, we can discuss maybe in the next session. Fine. Okay, just a second. Okay, fine. So I have a few plans in mind, but before discussing all those, I just want to, this is kind of an open session. So if you have any doubt in any part of the content in this week, please ask. And then I would be specifically dealing with one or two topics before wrapping up. Is there any doubt in any part? Okay, so all of you understood it. Great thing. So one thing that was that's one student actually asked in the previous session is that the time complexity of topological the time complexity of the longest path, right? Finding the, okay, I think it was longest path or topological sort, doesn't matter, they are kind of the similar algorithms. Longest path is essentially topological sort with a single change, that is this L path, this line. Other than that, it's basically topological sort on. Okay, so I would use the longest path, this particular code to discuss that. Okay, same code, this same as topological sort concept. See the time complexity, why it is actually order of m plus n, which is basically the order of number of edges plus the number of vertices. So you can see the idea is, if you simply see the loops now, if you check these loops directly, just make it a little bit bigger.
So before that, can you discuss the topological sort itself?
Okay, topological sort, fine. So okay, let me go over here. Draw it on. So see, let's say we have a graph like this. First of all, what is a what data structure you can apply topological sort? Okay, so we would start from there, and then we would discuss the other things. So what is topological sort? I would come to that later, but before that, on what kind of data structure you can apply the concept of topological sorting? Can you apply it on anything? Can you apply it on any linear, I mean, let's say a list, array, or anything, any kind of graph, right? You all have not learned about trees, so but shortly we will do that. So can you apply topological sort on any form of data structure, or let's say any kind of graph? That's the question.
No, sir, I don't think so.
Okay, so why?
It essentially applies on graphical structure, right? We can do it.
It requires a graphical structure, correct? So fine. So let's say I have a graph like this, the one that I'm drawing now.
Graphical structures which don't have cycles
Yeah,
and
exactly.
interdependencies.
Exactly. So structures which don't have cycles, that's why we call it directed acyclic graph or DAGs. Fine. So you can run topological sort on graphs which are directed, because without the sense of direction, there is no contradiction between the two. I mean, there is the concept of prerequisite that has been discussed in the lecture. Na? So that would not be there. I mean, that would be topological sort, but essentially it would not have the essence of topological sort or the meaning of topological sort. So you must have a sense of direction, or the sense of pre and post with respect to a particular vertex, which actually gives you the sense of prerequisite that has been discussed in the context of the lecture. Okay, so you need to have directed, number one, and then you must not have cycles. It should be acyclic. Why acyclic? Because what we are essentially trying to do in topological sort is we try to press the whole graph. So let's see if this is a graph. Fine. Fine. So let's say this is a kind of graph. In this graph, what we want to do in topological sort is we would actually put all the nodes of this graph in such an order, in a sequence, that the edges which are there, okay, assuming that there are no, I hope there are no cycles in this graph. Are there any cycles? No.
Oh, no,
Yeah.
sir.
No. Fine. So this is a DAG. This is a directed acyclic graph. On this, you can apply topological sort. Okay. And what is the idea of topological sort? So I'm not going for the exact sorting, just the idea that I want to discuss is, let's say A, B, C, D, E. Okay. Now assume this may not be the proper order. I'm just taking an arbitrary order and assuming it to be the topologically sorted order. But this is what the essence is. Fine. So let's say you have, I mean, one of the vertex you take, right, and whose in degree is 0. Now, what do you mean by in degree is 0? That means there is no other edges which is coming into that vertex. Can you give me an example of such a vertex in this graph?
B.
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 Correct. So B has in degree 0. So you choose B. Why? Because in degree here means an edge coming into it, right? And that essentially means some condition, some dependency, some prerequisite is there whenever an edge is going into a node that represents some dependent or some prerequisite that has to be catered about before actually accessing that node. So you must satisfy some condition. That condition is corresponding to that edge when it is entering into a node. So for such nodes where there are no edges incoming into them, they do not have any prerequisites. They do not have any condition that must be satisfied before you can access them. So we need that kind of node at first. So B is one such example. And I don't think there are any other node where in degree is 0. Yeah. But another important point is there can be multiple nodes at any point of your topological sort where the in degree can be 0. That's why when we would discuss in the code, you would see in this session only, we would shortly after this discuss the code. You would see that we are using a queue to keep a track of all the nodes at a point whose in degree is 0. Fine. You can use any of the nodes to actually calculate the topological ordering, and there are multiple possible topological ordering for a given graph. The only reason for this multiple possible topological order is that at any stage in the graph, you can have multiple nodes having 0 in degree. So depending upon whichever node of 0 in degree you choose, you get a different topological order. Okay. So what is topological order? Let's come to that again. So I choose B at first. Okay. And then what we would do is, so let's actually make the whole dry run only. So we chose B at first, and then the next step would be to remove all the edges which are going out from B. And that essentially means you would reduce the in degree of all the nodes to which there is an edge from B. Fine. So let's do that. What we would do is we would erase this vertex, this vertex, this vertex. In my that I have A, C, D, and E. Done. Now let's see which are the nodes which are 0 in degree. You see A has 0 in degree. C has 1 in degree because there is an incoming edge into C. And D also has 1 in degree. Right? E also has 1 in degree. So the only vertex whose in degree is 0 now is A. Right? So A would be the second one. Okay. So now third is, now let's delete the edges from A. So this we would delete. Okay. After that, now see which vertex has 0 in degree. E has 0 in degree. So is the third one in the sequence, and obviously after that we would delete the edge from E. And now I see D is the one which has 0 in degree. And then trivially C would come. Fine. So we have deleted all the edges. and this is the topological order that we got, right? But now let's do some rewind. So what is BAEDC, correct? Wait a minute. So undo does not work here, right? Okay, anyways. So BAEDC is the order that I got, the topological order. Now what does this BAEDC means? So this is my topological order. Topological order, and this in degree deleting thing, that whatever we did, that is essentially your topological sort. Fine. Now what does this sequence actually means, BAEDC? This actually means that in order to complete C, you must at first complete D. Okay, and before completing D, you must complete whatever is there on. So it's better to say it in the other way. So it's better to say, in order to complete C, you must have all of these covered. In order to complete D, you must have all these three covered. In order to complete E, you must have this whole thing covered, and in order to complete A, you must have B covered. Okay, that may not be the case in situations where in degree maybe there are multiple vertices with 0 in degree at one end, right? So that can be a situation. In that case, you, let's say B and A, either of them you can do, doesn't matter. But here, if you remember, there was a H from B to A. So in order to complete A, you must at first complete B. That is the only concept of topological sorting. And why topological sorting is important? Because the order that you get, that gives you the sequence of operations that you must do in order to satisfy all the constraints. What are the constraints? The constraints are the edges that we discussed. These edges, right?
So when we say complete, we essentially mean that complete all the edges or construct the entire graph. So we have to do it in this way. That's kind of mean.
Yeah. You have to basically, so each of these edges actually represent a constraint that you cannot. So if I have an edge from A to B like this, that means I cannot do the work B unless and until I complete the work A. That is the constraint. Now, if I make, using these constraints, if I make a complex graph, this easier, but let's say we have a very complex graph like this, then I ask you this question as a programmer, or let's say as a project manager. This is quite efficient in case of project management also, that I need these tasks to be done. In order to do this task, you have to be you have to complete these two other tasks. In order to complete these two other tasks, you must have completed this third task. You have a complex network of all these things, and then I ask you, tell me a specific order in which you would do the work, right? Or how many possible orders are there in which you can do the work. So topological sorted order actually gives you that answer. And there can be multiple orders of topological sort. There can be multiple, topological orders, and in either of them, you can actually satisfy all these prerequisite constraints and complete your task. That's the idea. Okay, so there is a very tight relationship between this topological ordering and mathematical concepts of poset. So have you all learned about partially ordered sets in maths? Maths 1 or maths 2, I don't know.
No, sir.
Okay, so relations functions you all have learned, right? Symmetric, equivalence, transitive.
Yes, sir.
Okay, so I'm not going into the details of that, but there is another two property with respect to relation, which is called asymmetry, okay, and antisymmetry. I'm just mentioning it because this is related. And asymmetry and antisymmetry, and others are reflexives and your transitive, and what was the other one? I just said, what is the name? Reflexive, transitive, and the symmetric property, symmetric property, antisymmetric property, and asymmetric property. So these are basically the properties of a relation, and this asymmetry property is actually used to discuss some a specific behavior of a relation, which we call partially ordered sets. And partially ordered sets actually give you this notion of direction, right? You should have a specific direction. In this direction only you should do the work. You should proceed from one node to other. So topological ordering or directed acyclic graph, this is quite tightly related with partially ordered set, and in higher algorithms we would actually use them quite a lot together. Fine. So if you are interested, you can check that also. So check these two words if you get spare time. These two, one and coset and has diagram. And try to relate it with the directed acyclic graph and topological ordering. Fine. Okay, so that is topological ordering basic idea. Now, one important point that I want to discuss over here only, see. So while making the dry run of this algorithm, what we actually did, every time we found the node which has 0 in degree, we actually deleted all the edges which are going out from that node. And accordingly, since we are deleting all that edges, we are reducing the in degree of the vertices into which those edges went in. Right, that's what we did. Simply take a 0 in degree vertex, remove all the nodes. As a result of removing, the in degree of some other nodes got reduced, and accordingly you get some other nodes whose in degree is now 0. Choose either one of them and again repeat the same task. So intuitively, see, what you are essentially doing is you are going through each edge of the graph and doing some constant amount of work. Is it correct? Because you are choosing a particular node, you are removing all the edges. Then you are choosing another node whose in degree is 0, and then you are removing the edges going out of that. So one important point that you must notice is you are removing the edges. So, but you are not using that edge twice. You are only removing it once. So if I remove this edge once while actually choosing B first time, I will never require this edge to be operated upon in the subsequent iteration of the topological sort. So this is removed. It's not there. Right? Then which I choose this one and remove these two. And let's say then I remove this one. So every edge you are removing once, and then you are simply doing some constant amount of work. What is that constant amount of work? That constant amount of work is just reducing the in degree of all the vertices to which those edges were coming in. Right? And then what is the next constant amount of work? That is simply picking any one of the vertex whose current in degree is 0. Right? So basically you're doing this task and you're doing it for each of the, basically you're doing it for each edge that you are getting in the graph, right? You are not working upon the same edge twice. So that's the intuition behind this order of E idea. Okay, and when we say order of E plus N, the reason for that is that is E plus N or M plus N, whatever, that is vertex and edges. The idea is, see, this order of E plus N is actually equal to order of N square, because this order of E can go up to order of N square when what kind of graph? When would this condition happen?
Complete graph.
Exactly. And it's
So
a complete graph.
why do we need to even include the, what do we say, number of vertices here? So this is, so it will automatically come for a complete graph.
Exactly. Why do we need to do that, right? When it is not a complete graph, when it is a sparse graph, so I think sir has mentioned it already. When it is a sparse graph, it's better to use a adjacency list. And when it is a complete graph, you can use a adjacency matrix, right? So you, in the topological sort algorithm also, what you would do is you would travel through the adjacency list every time and then find the in degree, do the whatever you want to do, right? Whether it is 0, reduce it by 1, all the tasks. But basically you are traversing through the adjacency list, correct? Now, what is the time complexity to travel the adjacency list, right? You may not do it for every iteration of the loop. You are actually checking the list corresponding to a particular vertex, right? Who are the neighbors with respect to that particular vertex? That's what an adjacency list is, right? It's something like this. If I draw a physical structure, So let's say these are the nodes, right? And corresponding to each one of them, I have a list which stores all the neighbors. And this is my key and this is my value, right? Dot, dot, dot. So this is an adjacency list. So in each for loop iteration, you are moving. So let's say you are checking the neighbor for I. So this is I plus 1. Fine. So first for loop is checking, first iteration of the for loop, all the neighbors of I. Then next iteration, it would check I plus 1th neighbor. Why? Because I plus 1 would have been in the queue and it would have been popped out at some point in the algorithm, right? It may not be I after I plus 1. That depends upon whether there is an edge from I to I plus 1. And when you remove I, whether I plus 1 becomes in degree equal to 0. All those conditions are there. But I'm just assuming you may not do it in the order I plus 1, I plus 2. Let's say you did this one, then some vertex over here, then some vertex over here. But essentially at the end, so this is what we call amortized analysis. Sir has used this now in the lectures. So you are not worried about the sequence of operation. You are just worried about the overall average. So what is the big picture? The big picture is it may not be in specific sequence, but at the end of the algorithm, you have traversed through the whole adjacency list. That would happen obviously because you are actually going through all the nodes while doing topological sort, right? So basically you would traverse through the whole adjacency list. Now, what is the time taken to do that? If you just answer that question, you would see obviously, since it may be sparse, that is the length of this list, that would be something very, very lesser than n, assuming n is the number of vertices. Correct? If it is a sparse, if it is dense, then obviously it would be equal to n. Or, I mean, you have or it's very close to n. But if it is sparse, it would be lesser than n. The length. Try to understand this. The length of this list, of all these lists, I mean, if it is a sparse graph, in that case, the length of this list would be very much lesser to n. Right? Number of edges are less. That means n is the number of vertex. So in this situation, what's happening? You have very few number of very few length list over here. So if I take the overall time to traverse this whole structure, first is how many rows are there? Obviously, the n number of rows are there, right? And then you have the total number of edges which are there. You have how many edges are there? That's on this value part of it, right? So you are actually traversing through all the value parts, right? So I'm just taking it to be E. Now, if it is a dense graph, this E goes to n square. So n plus n square would actually, since it is asymptotic complexity, it would always be n square. But if it is a sparse graph, then E is kind of in terms of n only. I mean, you can approximate it to be n or lesser than n. Okay, so it actually gives you n. So it rotates between these two complexities. Okay, so that is the intuitive idea, not the coding idea. Now, once we go to the code, you would again see that how this is true in terms of code also. This is how it is true in case of the dry run or in case of the the basic way the algorithm works. Okay. Yeah. So before moving to the discussion of the topological sort code, you want to ask anything?
So if a graph can only be either sparse or dense, so in that case also the only n or n square, these are the only two complexities that will exist, right?
At the end of the day, that would be, yeah, correct. At the end of the day, it would be between these two ranges.
Okay, so
yeah, that's what I wrote here, na? This sign, that it would vary between these two.
So we are going through n number of rows, and in each row we are checking the edges. So, but if so, why do we have to add e here separately? Like if we have to go through the number of rows, and so the amount of work is constant almost in each row. Will it be different? Like
no, it may be different. That's why I write e, right? I cannot write n because these lengths may not be same. So let's say this is 2, let's say this is 3 or whatever. But one thing that I can guarantee is when you consider the whole set of value, you would end up into E. Correct? I mean, each of these are edges, right? This corresponds to edge, this corresponds to edge.
Okay, sir. Yeah. Okay.
Right. If I sum this whole thing up, so if I do the summation of this, summation of, let's say our K, I mean our value, right? So let's say this is V. So if I travel from value equal to, let's say I start the index from 1 to the last vertex, which is my, let's say this is the nth vertex. So if I V1 to N, if I traverse and I do a summation of the values. So essentially this is the idea. Then this would end up in E. Because obviously each of this represents one edge. So I can have 2 edge over here. I can have in the next list, I can have, let's say 3 edge. In the next list, I can have, let's say 1 edge, only 1 edge. But if I do the sum of all this, I can guarantee you would get the total number of edge. That's the basic idea. Actually, you would, if it is undirected graph, you can get 2E, right? Because for every undirected edge, if there is an edge from U to V, that essentially means that if it is undirected, there would be an entry corresponding to U and there would be an entry corresponding to V. But if it is a directed graph, then obviously there would be only one entry corresponding to U and there would be no entry corresponding to V. So in case of undirected graph, it varies from 2E. So basically in undirected graph, it would be something like this. But it doesn't make any sense because there is a constant factor and asymptotic complexity doesn't consider. So ultimately, at the end of the day, again, this varies between n square and n, maybe 2n square, but this doesn't matter in undirected, right? Okay, is that clear?
Yeah, sure.
Okay, so now let's go to the code. So Sir has actually given a in detail dry run of the process that we just discussed with a much simpler example. Please go through it once. And now we would see the code. So one more question. So this is actually quite important. Before going to the topological sort code, this is what I want to ask. I have given you a graph, right? A normal graph is given. Now I want you to do topological sort in it. I have told you that in order to do topological sort, you must have a DAG, directed acyclic graph. So essentially you have to convert this graph into a DAG, right? Assume this is a directed graph only, huh? And then you can apply topological sort. So this we have discussed, the code part we will do now. But how to do this part? How can you convert a graph, directed graph, into a acyclic graph, directed acyclic graph? Anyone, please? Whatever comes to your mind, na, please say it.
So can you repeat the question?
How can you convert a directed graph into a directed acyclic graph? Basically, you have to eliminate the cycles. So how would you do that?
Remove the edges.
Sorry, can you repeat?
Remove the edges.
Which edge? How? I mean, you have to be very specific.
If there is any cyclic
Okay.
path, then we have to remove that edge.
Fine. How will you do that? I mean, I just want the exact way that you would do. I understand you have to remove cyclic path. So if there is cyclic path, you remove the edge to make it acyclic. Understood. But how would you do that? What is the algorithm that you would use?
So you can start removing edges at random, and once you can keep checking, like if the time every time, like if we remove the graph until the time we can disconnect it, we can maybe check something in between.
Great. Now that's the way with algorithms is, now once you said the idea, let's analyze it. Fine. So you say randomly we can remove some edges and let's see whether it is connected as well as it is acyclic. We have to check connectedness. I cannot just make a vertex make disconnected. So I have to keep it connected, correct? And also I have to ensure that there are no cycles as well. Got it. So now let's analyze how much time that would take. So let's say there are e number of edges in the graph. You want to choose any one of them randomly, right? So how many ways you can do that? Obviously, if there are e number of edges and you can choose any one of them, and then in the next iteration you can again choose any one of them, right? So first choice you can choose e number of vertices, sorry, edges. Second choice you have removed one, so again there is a cycle, so you check for e minus 1 number of edges. Third, you check for e minus 2 and again found the cycle, and you have got e minus 2 number of choices to choose, right? Dot dot dot. Let's say it goes up to k, right? And let's say if this is a highly cyclic graph, and at the end also you need a, I mean, you get this kind of cycle only, so you can actually go up to not 1 but something up to 3, because there is, for a minimum cycle you must have 3 edges, right? So it is only, see, if this is kind of e factorial, not e factorial, this is greater actually, but it is very tight upper bound, very tight lower bound of e factorial. Only it is lesser by 2, I mean 2 times, because only 2 would be coming here, that's it. So this number would be very huge. It is basically order of e factorial, your algorithm, just to choose, and then you have to again check whether it is cyclic or not. Fine. So if it is a dense graph or a complete kind of graph, so this is something like this, right? I mean, it would take ages to do. Got the point?
Yes, sir. Understood.
So what you would do? So the answer remains in the normal algorithms that you have learned, and sir has discussed this also, but it's little subtle to observe. See, you can use BFS, DFS, either one of them. Okay. The thing is, you can use BFS or DFS to find cycles in a graph if it is a undirected graph. Directly you can use just with one change in condition. Okay, so that's a homework. How can you find cycles in a graph using BFS, DFS? Try to think of that. There is only one if condition that has to be modified to check that whether there is a cycle in the graph or not. Okay, so please try to think about that. But if you have a directed graph, you cannot directly use BFS, DFS to check for cycles. The reason for that is, in case of an undirected graph, this is a cycle, right? But in a directed graph, this is not a cycle. Correct. So that the notion of direction actually, even though this looks like a cycle, it is not a cycle, and that is because the direction is making it happen, right? It's not letting it to be a cycle. So you cannot use direct BFS, DFS in a graph to check for cyclicness. Rather, you have to use another technique which has been taught, which is the pre-post numbering. Right? Sir has taught that. So before you push into the stack, so let's say I do it by DFS, right? Okay, so at first you print whatever node you got. Fine, I'm just writing a kind of pseudocode kind of thing. So at first you have the A list and all the other parameters over here. So at first you print it, then you make it visited, right? That is done. And then you basically check for neighbors for I in whatever A list of my node, right? And in whatever, what is the next thing that you do? If it is not visited, if visited of I equal to false, you simply call DFS on the ith node, right? This is the basic pseudocode of a DFS. Now, sir has discussed in the pre-post numbering how to use that. So before, I mean, so here when you are getting the node over here, right? When you actually in the DFS, here you are actually taking the node out of the stack, right? So here you would actually use pre equal to a count variable, and make count +1. So I would just check the, see the, discuss the code, but before that, just the idea. Okay. So count +1 you do. And when you are popping it out, right? Just when you are popping it out. So when a particular node would be popped out, so corresponding to this node. So here I have got the node, right? You are pushing all the neighbors of that particular node into the stack. What is stack? Stack is this DFS call, right? When you are calling a function, then essentially it is moving into the stack frame, stack call. So are you guys clear about that concept? When you call a function, it is actually into a stack frame. Is that discussed in the Python or in any CT or something?
Can you just do it again once?
Okay, so basically what happens is I have not used any stack in this program, right? No stack, right? There is no stack. I am just calling DFS. So when you do recursion, so this is essentially recursion, right? So when you do recursion, what happens is every time you make a recursive call, or not only recursive call, even every time you call a function, there is internally a system stack. Okay, there is a system stack. System stack. What happens is, so let's say there is a main function in Python, right? And I have started the program from main. So the first DFS call was done from the main function. So main was called at first, right? So main would be at bottom. Then let's say I called DFS for the first time. So I'm denoting it by DFS1 on say some vertex V. And DFS I'm doing recursion in the DFS code, right? So let's say this recursion is the second recursion. So DFS2 would come here. The second recursive call on the other vertex V dash, right? Where V dash is neighbor of V. Correct. This is V dash. Yeah. Where V dash is neighbor of V. And that's why you got V dash as an unvisited vertex over here. And then you call DFS on V dash, which is this DFS. So like this, you would proceed with subsequent calls. And there would be at some point when there are no more vertices left which are unvisited, right? And then what would happen is, let's say DFS K is that iteration on some VK, right? Where there are no further vertices left which are unvisited. And now it would pop. So then, stack push and pop happens, right? So now this particular stack frame, which was called at last, it would pop out. And once it pops, now the control shifts to the immediately next, the next stop, right? Which was DFS K-1 in the recursive chain. So this would be popped. So like this, every one of them would be popped until and unless the control shifts to main. And finally, the main function is also popped and your program terminates. So this is how a normal program works. And not only in case of recursion, if you call, say, let's say F1 function is there, in which you are calling F2 function, in which you are again calling F3 function, right? So, and all of this started from main. So main would be at bottom in the system stack. Then F1 would be there, then F2 would be there, then F3 would be there, like this. And once F3 finishes its work, right, it would come back to F2 because F2 has called F3. Okay, now F2 after that, if it has any task left, then it would complete that task. So what I mean is, so let's say inside F2's definition, now let's say here F2 is defined. F2 is defined over here. And inside the definition of F2, there are a few lines of code, and then you are calling the F3. F3 is defined over here. Okay, some lines of code. And after that, there are some other few lines of code under F2, and then F2 ends over here. Similarly, F1 is calling, let's say, F2 at first, and there is some other lines of code after that, and then F1 is ending. Right, now main is calling F1, so main would be at bottom of the system stack, then F1 would come. As soon as F1 comes at this line F2, it would directly call F2, so F2 stack would be pushed on. See, these lines are not yet executed by F1. F2 was coming first, right? F2 call, so F2 would be first formed on the stack. F1 has yet not been finished. It is still pending the execution of these two lines, but F2 is called at first because that is earlier line. Now F2 is called, so F2, the control shifts to F2. F2, it would see these two lines, it would execute these two lines, and then F3 is called. So F3 would frame would come here at the top. Okay, now F3 does not call any other function, so it would finish its task. So F3, once it finishes its task, it would be popped from the stack, and the control would shift to F2 again. Now it would see, after calling F3, was there any other task left inside F2? Yes, these two lines were left. So these two lines would be executed after that. And after that, F2 finishes, right? So again, F2 would be popped out and come back to F1. Why? F1 was the one who called F2. So after F2 was called, is there any other task left? Yes, these two lines are left under F1. So then F1 would execute these two lines. And then finally F1 also pops out and goes to main, and then main pops out and terminates the program. So this is a basic structure of how a function call happens. So you see, this is a stack, right? So whenever you are using recursion, you are actually using a stack. Now you know from the lectures that in order to make BFS, you have to use a stack. In order to use BFS, you have to use a queue. Okay, so what we are doing by in this pseudocode, when we are actually recursively calling DFS function, and that's how the DFS code is written in this case. So DFS, we are not exactly using a stack separately, but this recursive call implicitly makes it like a use of stack. Okay, so with every DFS subsequent call, you are actually traversing through the graph. And when you are actually hitting a point where there are no other nodes there to visit, so let's say there is a graph like this, okay, and you have started from here and you are currently at this position. Okay, so this is visited, this is visited, this is visited, this is visited, and you are not able to go at any other path from here. So you would come back from here to here. Okay, and then again come back over here, and you would see that this is left, so you would also visit this one, and then you would again come back here and move out of it. Okay.
Sir.
Yeah.
Sir, in this function example, the recursion terminated in the F3 function, right? So why would the other lines of F2 be executed when F3 rolls back after its completion?
Because that is left, right? F3, whenever you check a line, so in F1 as well, you see the same behavior. F2 was here. So after that, two lines were left. So until and unless F2 completes its task and return backs over here, the control return backs over here at the end of the call of F2, these two lines would not be executed.
But sir, the other two lines of F2, they would be something like an else condition, right?
It can be anything. It can be something related to the call of F3. It can be anything. There is no compulsion.
But if suppose there's something like an else condition and it actually turned out true, so like why would they execute when F3 rolls back? Because if it terminated in F3.
If it is an else condition, then it would not be executed. It's just like programming logic. If let's say F3 returns a value, okay, and depending upon this value, these two lines would be executed. It may be a else condition also, or let's say you call if something, then you call F3, right? Something like this. Else you would do something, right? If that is the case, then after F3 is called, if this else part would not be executed. Okay, idea that I wanted to give is this does, so main idea that I wanted to discuss is, if you have F3 function and let's say you have some other lines also in the F2 function as well, So it does not mean that these lines would be executed at first and then only you go to F3. It's not like that. It's just like the normal sequence. Once you encounter F3, you don't see these lines. You go to F3 at first, complete the execution of F3, and then you return back over here, and then you execute these two lines. But if it is a else statement, or if it is some other programming construct which depends upon the conditional execution of F3, then these two would not be executed. So that there you are correct. Fine. Okay, so my main focus was that if you write a DFS now, so it would be something like this, the basic code. Fine. And this is actually using a stack, the system stack, using the recursion. Okay, so when you use this, and you have to use pre-post numbering in order to find cycles in the directed acyclic graph, that was the main point. So you use pre equal to count when you are actually, before pushing the neighbors of a particular node, you assign the pre value for that node. And once you have explored all the neighbors, where you have completed exploring all the neighbors for a particular node, after this for loop is over, right? Because this for loop is actually traveling through all the neighbors of a particular node, right? So once this for loop is over, outside of it, you can write the post for that particular node, right? Okay, so here it should be P for that particular node. The post for that particular node to be again count, and then you can write count plus 1. So what you are exactly doing over here is, so what you are exactly doing over here is you're using a counter to keep track of the number of push and pops in terms of the neighbor of a particular node while you are actually iterating through the DFS algorithm. So what I mean is, if I take a graph and discuss this same concept, okay, so yeah, so let's say I have a graph like this. Okay, and my starting vertex is, let's say, A. Fine. So how would DFS, what is one possible ordering of DFS? So I can start from A. Okay, and since I am starting from A, my pre number, and this is my post number, I'm writing it like this. The left one is pre number, the right one is post number. Let's call it PO. So A would be there. A would be, since A is the first one to be pushed into the stack, it would be 1, because A is the one where it is starting. Fine. After that, what is one possible neighbor? C is one possible neighbor of A. It's fine. So I would go to C. Okay. Have I written the post number of A at this point? No. Why? Because A is not yet popped out. Okay. I would write the post number of A when A is popped out of the stack. Which stack? That system stack, recursive stack. Okay. And when that would happen only when I have exhausted traveling through all the neighbors of A. Okay. I have not yet done that. I have just reached C. So let's see what happens. So pre number of C would be 2. Right? Because next C is pushed into the stack. Right? Basically, this is equal to the inside the for loop. This part is same as inside the for loop. You are calling DFS on C. That's it. Okay. So what would happen next? Post number of C, I don't know, because I have yet not done anything. So now I would check who is the neighbor of C. Right? Next task. So who is the neighbor of C now? Are there any neighbors of C that I can go to? No. There is no edge coming out of C to any other edge. So it's a dead end. So that means what? the stack frame would be popped, right? We discussed that once you execute the loop and there are no further neighbors with respect to a node, what you would do is you would actually, that stack frame would be popped out. The function corresponding to the DFS of C would be popped out, right? So that means it is popped out from the stack since there are no further neighbors to go to. And now I would write this popped out, the post number of C to be the next value, which is 3. Fine. So, okay, now C is gone. So once the C is popped out, we discussed that once F2 is popped out, it would come to F1. Once F1 is popped out, it would come to main, right? So it always comes to the parent which called it. So C was called by A, so it comes back to A. Correct. Now when I come back to A, I see that what are other possible neighbors of A. That is basically the for loop, second iteration of the for loop. So we had this now for I in A list of node. This node is currently equal to A, right? And this I is actually my, initially it was C, and now I am searching another one. That is the second neighbor of A. But will I find any other neighbor? I see we have no other edges coming out from A and going to other vertices. So since there are no further edges, right, what we would do is now A would be popped out. Okay, now what is the value? It would be 4. So it's not reachable. Now if you do a depth first traversal, right, what is the difference between depth first search and depth first traversal? So depth first search only starts from a particular vertex and goes through all the reachable ones. Now what traversal does is, traversal is just calling the depth first search in a loop where you would go through all the unvisited vertices, and if there is a vertex which is not yet visited, you will again call DFS on that. So basically for vertices V in the list, right, A list dot keys, if I check if visited of V is equal to false, right, what we, sorry, not this one, visited of V is equal to false, you just call DFS on V, right? So what would happen if it, so we are calling DFS unless and until you traverse all the vertices. It may be that from a particular start vertex you could not traverse all the vertices, like in this case you could not go to B, D, but in the next iteration of this for loop, you could, this visited V corresponding to B, this, the value of visited B would be false, and then DFS of B would be called. So this is depth first traversal, that you traverse all of the vertices. That is basically calling DFS multiple times on all the unvisited nodes. So if you do that, then you would get another tree over here from where B will start, and B would actually go to C, but C is already visited. So again, it checks whether there are other nodes. So there are no other nodes to go from B to D or anywhere other. So again, it pops out. So the pre number of B would be 5, post number would be 6, no other place to go. And finally D would also come into the next call, and pre would be 7, post would be 8. Fine. So this is the basically pre-post numbering, how it would work. Okay, I request all of you to please watch the lecture once again where pre-post numbering is discussed, and then think of this discussion that you did now. Okay, it would clear the concept. So now the idea is, once you understand this pre-post numbering, how this is working by using the stack, push and pop into the stack, now I would segregate all the edges of the graph. You understand that this is an edge, right? I got from A to C. This line here means, I mean, I could push C starting from A into the stack. The reason for that being, I had an edge from A to C, and that's why C is a neighbor of A. So what we would do is, corresponding to each edge in the graph, once we have the whole pre and post list ready, sorry, not list, dictionary, pre and post dictionary ready for both A, B, C, D, whatever the value is. For A it is 1, B it is 5, C is 2, right? Whatever, like this, and accordingly A, B, C, D post. Once we have these two dictionaries ready, what we would do is we would check each graph. We would check each edge of the graph and see what is the pre-post of A. I mean, what is the pre-post of the starting vertex and the ending vertex. So for every edge in G of form UV, then you check what is the pre of U and the post of U and pre of V and post of V. Check pre of U, post of U with pre post of V. Fine. Now we just tell you three conditions. Right. Number one condition, if pre of U, so I'm writing pre and post as PU. If pre post of U contains, now this is there in the slide, I'm just writing it, contains pre post of V. That means if you check from here, this example, take this example. Right, sorry. So what is the pre-post of A? It is 1, 4. What is the pre-post of C? It is 2, 3. You see that this 1, 4 is containing 2, 3 because after 1, 2 comes and then 3 comes and then 4 comes. So this is between 1 and 4, this whole set. Right. So there the edge from A to C, here A is my U and C is my V. Right. So the pre-post of U is containing the pre-post of V, and that means this is a forward edge. We call it a forward edge. Forward edge. Similarly, we would again see pre-post of UV for all the edges, and you would find what are the conditions. First condition is pre-post of U contains pre-post of V. Second is pre-post of V contains pre-post of U. Pre-post of U. And third is disjoint, that none of them contains the other. This is forward edge, this is called back edge, and this is called cross edge when they're disjoint. In order to convert a graph with cycles into a acyclic graph, only thing that you have to do is you have to check this pre-post number, and whenever you see the condition of back edge is getting satisfied for a particular edge, remove that edge. That's it. So in order to remove cycles, only back edge must be deleted from the graph. How can you find back edge? By simply checking this condition, whether the pre-post of V contains the pre-post of U. So if there is an edge from U to V and the pre-post number of V is containing the pre-post of U, in that case it's a back edge. If there is an edge from U to V and the pre-post of U is containing the pre-post of V, that is a front edge, that is totally fine. Forward edge, sorry. Okay. But if V contains U, then that's a problem, that's a back edge, and you must delete it. Once you delete it, simply delete these two, this edge. Once you delete that edge and you delete all the back edges from the graph, then whatever is left over, that is a acyclic graph. Now this would take again order of E plus V time, because essentially you are traveling each edge and checking the pre-post value for the two incident vertices. So this would turn up to be an order of E plus V algorithm again. Fine. So that is very important, how you can check the pre-post number and convert a graph into a cyclic graph. Now, once you convert into an acyclic graph, the way we discussed topological sort, you can simply apply that topological sort. Okay, any doubt in this?
No, sir.
Okay, I know it may be a little bit confusing. I just request all of you to again watch the lectures where pre-post is discussed. This is the most important concept, I believe, in this week, because this is a great tool when you do some other code. I mean, if you do coding further, this pre-post numbering would come up every time. TFS along with pre-post. It helps you in checking strongly connected components, and a lot other things. Okay, please understand this concept of pre-post. It's very important. Okay, so now topological sort was the code. It would not take much time. Just I would discuss that and then in the session. Yeah. So see what's happening in topological sort. What we did was initially, at first, we have to set the in degree of all the vertices. So this is the initialization phase, right? You simply set the initial in degree of all the vertices to be 0 at first, and then according to the A list, that is the adjacency list, you set the in degree accordingly, right? For every vertex in the adjacency list of U, that is for every neighbor V of U, you set the in degree of each neighbor by increase the in degree of the neighbor by 1. Right. So this is basically initialization. Set the in degree to be 0 initially and then traverse through the adjacency list to set the in degree of each vertex accordingly. Now, once that is done, this is the main algorithm, this part of topological sort. You essentially make a queue, okay, and you check whether the in degree is 0 or not of a particular vertex. If the in degree is 0, you add that in the queue. So this queue is, as the name suggests, it's a 0 degree queue. So basically this queue would contain all the vertices which has in degree 0 at any point of time in the code. We discussed that there can be multiple vertices with 0 in degree, right? While we are going through the topological sorting. So this queue would store all the vertices at any point of time in the code which has 0 in degree. So this is what we are doing over here, you see. Simply we traverse through the adjacency list keys and check whether the in degree of the key is 0 or not. If it is so, add that key in the queue. Fine. So now we have a queue with 0 in degree vertices. Okay. And what is the work that we need to do? We would just go on checking all the 0 in degree vertices, and then when there are no vertices left, then we would quit the algorithm. So same thing. If the 0 in degree queue is empty, then you quit the algorithm. Unless and until it's empty, you continue the while loop. You pop just any one of the vertices from the 0 in degree vertices, right? And then simply add it in the sorted list order, right? As we did. I mean, you have to you have to get the sorted order, right? So if J is the first vertex which is chosen for 0 in degree, then that means it is the first one in the list, first one in the sorted sequence. So you put that in a list to just store the sorted sequence. So toposort list is just the list to store the sorted sequence. And then simply, since J is being considered here as the first 0 in degree vertex, you actually remove all the edges from J and then reduce the in degree of all the vertices which had an edge coming out of J into itself. Correct. So that's why here this line actually you can it's not required, because this is what it is doing essentially is this line. Understand this line properly. Huh? This is not reducing the in degree of the vertices which are neighbor to J. It is itself reducing the in degree of J. Why it is so? Because see, the condition for 0 in degree is there now. So since we are not moving J out of the list, so we are making the in degree of J to be -1 by this line. So next time it would not be considered when you check for 0 in degree. That's it. Fine. This in degree k equal to 0 will condition would fail when you check this. So if you remove J, then that is also fine. That you may not actually write this. So okay, so once you get the J, then you check for all the neighbors and then you reduce the in degree of that neighbor. Now you see in degree k equal to in degree k -1, right? The one we are doing. And if the new in degree that you got for the particular neighbor is 0, then you simply add that in the queue. That's it. Same thing. So just if you see this code and think about the algorithm that we just discussed, right, before the pre-post discussion, the same, it is by line the same thing that you are doing. Okay, take from Q one of the nodes, check its neighbors, reduce the in degree of the neighbor by 1, right, for all the neighbors who, I mean, which had an edge coming out from J to that particular node, and that's why it is neighbor actually. So reduce the in degree of that by 1. If the in degree is 0, add that to Q, right, because you need the next set of vertices whose in degree has become 0 because of reduction in the in degree. Okay, so you complete this process and you can then return the topological sorted list. Okay, so this is again explained that basically you are traversing this list, right, every time. So this is order of one operation, this is order of one operation, this is order of one, this is order of one, this is order of one, adding to a queue. All of these are order of one. Only thing that matters over here is this line, that basically you are traveling the list unless and until this while loop is getting empty. This while loop will get empty after it traverses all the edges after it traverses all the vertices in the graph. So basically for all the vertices, you are actually checking the neighbors. So that means your neighbors mean the edges, right? And this is all the vertices. And that's why you get this edge plus vertices in the complexity. Same thing that we discussed just earlier. So if you get one concept clearly, you would be able to relate all of this together. So I would request all of you to please again see the lecture and maybe again the live sessions, skip the parts and just see the parts that you feel you need to check once again. And then you can, if you have any further doubt, you can post on Discourse. Yeah. Okay, so any doubt regarding this, or otherwise we would wind up the session. Okay, no doubts. Then thanks a lot for everyone joining. Yeah.
Thank you, sir.